Hello friends. Okay, in the chapter disposal of wastewater, in the first two, 3 lectures, we have studied about the how to dispose the wastewater and what is going to be happen in a stream when we are disposing in a nearby stream. Is it? So that we have studied, and we have studied how the dissolved oxygen Sag curve is going to be obtained when we are disposing a wastewater. So once again, within few minutes I will repeat it. So I told you this will be the stream. This is the point where you are disposing the effluent, and at that time it will start decreasing the level of dissolved oxygen. At the same time, due to reaeration process, the dissolved oxygen level is also simultaneously increasing in the same stream, and because of that a such type of curve is being obtained, and this curve is known as the dissolved oxygen Sag curve, DO Sag curve. Sorry, this we have studied in a last chapter, last lecture. So same in a proper format I am going to explain you. We are going to study today, that is the oxygen Sag analysis. We are going to study oxygen Sag analysis. Okay, so I will draw the dissolved oxygen Sag curve once again. So this will be the amount of DO present, or we can say DO in milligram per liter, against that distance, or we can say this is the time. It may be whatever may be there. So when this is the spot where you are disposing the effluent into a stream, and at that time it will start showing such type of deoxygenation curve that we have studied. This is known as the deoxygenation curve. Deoxygenation curve. And at the same time, deoxygenation curve obtains. Why? Because we have disposed the effluent which is contaminated with BOD, and that is nothing but the organic waste impurities are present into that, and along with this microorganisms are also present, and these microorganisms are going to be consume the oxygen present into that stream for the decomposition of organic material. Is it? And hence the level of that dissolved oxygen in that particular stream starts depleting. That is known as the deoxygenation curve. But at the same time, the atmospheric activities are going on. Wind is blowing, sun is traveling there, and radiations towards this surface of this stream. That is nothing but the re-aeration is also going to be happen, and hence the level of dissolved oxygen is increasing into the same stream, and it obtains the curve is known as the re-oxygenation curve. This curve is known as the re-oxygenation curve. So outcome of these two activity, we are getting obtain the dissolved oxygen Sag curve. Is it? So this we have studied. So we can say this is the DO Sag curve. Now we are going to analyze the DO Sag curve. So I told you the level of dissolved oxygen in that particular stream. So this I have shown the saturation level of dissolved oxygen. Saturation level of dissolved oxygen of that particular stream. But it is not necessary to have the dissolved oxygen saturated when we are disposing the stream is saturated with the dissolved oxygen, it is not necessary. It may have some initial dissolved oxygen deficit. It may have some initial dissolved oxygen deficit because of upstream activity, some other activity, some other type of effluent may have disposed, and because of that it may have initial dissolved oxygen deficit. What is meant by dissolved oxygen deficit? The amount of oxygen present into the stream, whether it is saturation, there is no dissolved oxygen deficit, but if the dissolved oxygen is less than the saturation level of the stream, that is known as the dissolved oxygen deficit. Is it? How to calculate the dissolved oxygen deficit? That equation we have studied in last lecture. Dissolved oxygen deficit, D, can be calculated as saturated level of DO minus actual level of DO is nothing but the dissolved oxygen deficit. So it may have the dissolved oxygen deficit at a different place, different dissolved oxygen deficit. So if we are considering with respect to time, then initial dissolved oxygen deficit, we will give the notation D naught. Dissolved oxygen deficit, we have given the notation D. Okay. Then when at any time, if you will calculate the dissolved oxygen deficit at any time T, in that case we can say it is the dt. We will give the notation dt. And one more point we have discussed, the critical dissolved oxygen deficit, that is DC, where at the critical time, the time with respect to that will be considered as the critical time TC. This will be time T. Are you getting? So at critical time, the level of dissolved oxygen is critically low, or no dissolved oxygen is present, or we can say minimum dissolved oxygen level is present, is nothing but the critical dissolved oxygen deficit, that is DC. Is it? So when the sewage is entered into this stream, it is having there the organic impurities or BOD. Is it? Initial BOD, that is nothing but the L naught. And with respect to if it is at a particular time, that will be noted, the notation will be given as a LT. Is it? So we are going to study the analysis of dissolved oxygen Sag curve. The dissolved oxygen Sag curve analysis is possible, easily possible, by superimposing the reoxygenation curve and deoxygenation curve. Sorry, this is the deoxygenation curve and this is the reoxygenation curve. If we will superimpose these two curves, it is easily possible to determine with the help of Strater-Phelps equation. With the help of Strater-Phelps equation. So we are going to study that Strater-Phelps equation. To determine the dissolved oxygen or to analyze the DO Sag curve. So when we can write that we are superimposing the DO Sag curve, reoxygenation Sag curve, reoxygenation and deoxygenation curve. So same we can write in a mathematical form, that is d dt upon dt is equal to F. F is nothing but the deoxygenation and reoxygenation. Okay, or we may rewrite this equation, d dt upon dt is equal to k dash into lt minus r dash into dt, where dt, just now we saw that the amount of dissolved oxygen deficit at any time t in a stream. Is it? R dash is nothing but the reoxygenation constant to the base E. Then K dash is the deoxygenation rate constant to the base E. Then d dt upon dt is the rate of change of dissolved oxygen deficit. It is the rate of change of dissolved oxygen deficit. Okay, now LT. About LT, we have studied in the chapter number 1 while studying the chemical characteristics of wastewater. In chemical characteristics of wastewater, we have studied one of the characteristic as a BOD. And in BOD is nothing but the biochemical oxygen demand. And while studying the chemical characteristics, we have formulated the first stage BOD. First stage BOD. And while formulating the first stage BOD curve, we have determined the equation for LT. LT is nothing but the amount of first stage BOD remaining at any time t. And that equation we have determined as LT is equal to L naught into e raised to minus k dash into t, where t is the time in a day, k is the deoxygenation constant to the base E, and L naught is the amount of BOD remaining at time t is equal to 0. Or we may write this equation LT is equal to L naught into 10 raised to minus k into t, where t is the time in a day, k is the deoxygenation rate constant to the base 10, L naught is the amount of BOD remaining at time t is equal to 0. Is it? So we will give the equation numbers to this. I will give this is the equation number 1. Okay. And this will be the equation number 2. Okay. Now we will rewrite this equation d dt upon dt is equal to k dash into LT minus R dash into dt by putting the value of LT is equal to L naught into e raised to minus k dash into t. So I will rewrite this equation d dt upon dt is equal to k dash into value of LT, we will put it here as L naught into e raised to minus k dash into t minus R dash into dt. Okay, or we can rewrite this equation d dt upon dt plus R dash into dt is equal to k dash into L naught into e raised to minus k dash into t. So this has become the equation. We will give the equation number to this equation as equation number 3, and this is the first order first degree differential equation. This is the first order first degree differential equation. And if you will solve this first order first degree differential equation with a standard procedure, you will get the value of dt. So I will write that value of dt directly, as you will get this equation after solving this equation number 3 with a standard procedure as dt is equal to k dash into L naught upon R dash minus k dash into bracket e raised to minus k dash into t minus e raised to minus R dash into t bracket complete plus d naught into e raised to minus R dash into t. So this kind of equation you will obtain. I will give the equation number as a 4, or this is the equation with respect to base E. Okay, so or we can write this equation dt is equal to k into L naught upon R minus k into 10 raised to minus k into t minus 10 raised to minus r into t plus d naught into 10 raised to minus r into t. So I will give this equation number as a 5. So these two are the equation, Streeter-Phelps equation. This is the Streeter-Phelps equation. to determine the dissolved oxygen deficit at any time t, you can determine the dissolved oxygen deficit at any time t. Is it? So with the help of this equation. Now we can find out the critical dissolved oxygen deficit DC. We can also determine the critical dissolved oxygen deficit, where we have here in this figure the dissolved oxygen deficit at any time t we can determine with the help of this equation. Now if you want to determine the critical dissolved oxygen deficit at critical time, how to go for that? So critical dissolved oxygen deficit we can determine by putting the value of d dt upon dt is equal to 0. Is it? So that if you will put the value of d dt upon dt is equal to 0 in equation number 2, which is the equation number 2. So this is the equation number, in equation number 3. We will have to put it the value of d dt upon dt is equal to 0 in equation number 3, and that dt will be converted into dc. Then we can determine the value for dc. So I will rewrite this equation: d dt upon dt plus r dash into dc plus is equal to k dash into L naught into e raised to minus k dash into tc. It will be, that t becomes tc. Okay, now that we have kept it 0, so r dash into dc is equal to k dash into L naught into e raised to minus k dash into tc, or this equation will become finally dc is equal to k dash upon r dash into L naught into e raised to minus k dash into tc, or dc is equal to k upon r into L naught into 10 raised to minus k into tc. So I will give the equation number 6 and equation number 7. So with the help of these two equations, we can find out the critical dissolved oxygen deficit DC with respect to time Tc. Okay, then what is the Tc? How to determine the Tc? Tc is nothing but the time required to reach at the critical point. Tc, what is the Tc? Tc is the time required to reach at the critical point. So this Tc, time required to reach at the critical point, is it? So that is nothing but the Tc. So how to determine that Tc? We can determine the value of Tc by differentiating the equation number 4. So where is the equation number 4? We have, so if we will go to differentiate this Streeter-Phelps equation with respect to time t, and by putting the value of d dt upon dt is equal to 0, then we can determine the equation for Tc, and that equation we will obtain as Tc is equal to 1 upon r dash minus k dash into log to the base e into r dash upon k dash into bracket 1 minus d naught into bracket r dash minus k dash upon k dash into L naught. Okay, or we can rewrite this equation: Tc is equal to 1 upon r minus k into log to the base 10 into r upon k into bracket 1 minus d naught into bracket r minus k upon k into L naught. So we can determine the Tc also. Tc is nothing but the time required to reach at the critical point. Okay, so the relation between Tc and Xc is the time required distance. If we can draw the same graph, but with respect to time instead of with respect to time. If you will draw with respect to distance, in that case I will show with another color pen. If I have here, so if we will take the, instead of time, if we will take the distance, dissolved oxygen against the distance, in that case the dissolved oxygen deficient at any time t and the critical dissolved oxygen deficient at a distance xc, and the dissolved oxygen deficient at the distance x, is it? So that is nothing but the xc at a particular distance. You can take the example. Once again I will explain with this figure that this is the stream. In the stream, you can take any river for the study and you can analyze the dissolved oxygen Sag curve of that particular stream. And when you will go to analyze, at that time when you are disposing the stream with respect to time or with respect to distance, you can find out the dissolved oxygen deficient. So now we have discussed about with respect to time. Now we will discuss about the distance. Distance is nothing but the xc notation we have given. So we know the tc, how to calculate tc. Then the relation between tc and xc is equal to tc into v. V is the velocity of flow. Velocity of flow in meter per second. Velocity of flow in a meter per second, is it? And time required to reach, it is usually taken as in a day, is it? Now we will see, this is about the analysis of dissolved oxygen Sag curve. Now we will see with the help of one example how to determine the dissolved oxygen deficient at a particular spot. Okay, so I have written one example here for your to save our time. I have written already. I will read that example. This is the example. A stream saturated with DO has a flow of 1.2 meter per second, BOD 4 milligram per liter, and rate constant 0.3 per day. It receives an effluent discharge of 0.25 meter cube per second, having BOD 20 milligram per liter, DO 5 milligram per liter, and rate constant 0.13 per day. The average velocity of flow is given to you 0.18 meter per second. Calculate the DO deficient at point 20 kilometer and 40 kilometer downstream. Assume that the temperature is 20 degrees Celsius throughout the stream and BOD is measured at 5 day. Take saturation DO at 20 degrees Celsius as 9.17 milligram per liter. Is it? This is the example given to you. Now we will solve this example. So first I will note down the given data to avoid the confusion. Actually in a exam usually it is given in a tabular form, but for your understanding I have taken this kind of example. One more example we will solve in a tabular form. Okay, so from the question paper. So this example, a stream saturated with DO. So first of all, let me make you to read once again. A stream saturated with DO has a flow 1.2 meter cube per second, BOD 4 milligram per liter, and rate constant 0.3 per day. Up to this is the data about stream. Okay, it receives effluent. After that, the data is given about the effluent. Two different quality of water is there and two different characteristics are there. Accordingly, we have to separate it out. So first we will concentrate for the first paragraph, that is the quality of characteristics of the stream. A stream saturated with DO. DO saturated. It is written here saturated with, means there is no initial dissolved oxygen deficient. Saturated with DO is, saturated DO here it is given 9.17 milligram per liter. Okay, then has a flow 1.2 meter cube per second. Flow, it is 1.2 meter cube per second. It is the flow of stream, is it? So I will give the notation QS. Okay, then BOD of 4 milligram per liter. So BOD we usually give the notation Y. BOD, again that characteristics of stream. So again I will write the S, BYS is equal to 4 milligram per liter, is it? Then we will see, and rate constant. This is the rate constant of stream. Stream, what is stream rate constant? It is usually reoxygenation. So it's a, we will take that R is equal to 0.3 per day. Is it 0.3 per day? Now the next, this is the first half. Now next, it receives an effluent discharge QE. Is it? Discharge 0.25 meter cube per second. Is it? Then having BOD. BOD is the YE. YE is the notation given effluent. This is about the stream. This is about the stream. This is about the effluent. So I have given the notation E. YE is equal to 20 milligram per liter. Then DO is given, DO of effluent is given 5 milligram per liter. Is it? Then rate constant, what kind of rate constant will be here? It is effluent, so it will be a deoxygenation rate constant. So K is equal to 0.13 per day. The average velocity of flow, velocity is given to you, V is equal to 0.18 meter per second. Calculate the DO deficient at 20 kilometer and 40 kilometer downstream. Is it? And BOD, measured BOD is of 5 day. So Y5. So to that we will give the notation Y5. Is it? Now first of all, what we have to calculate? We have to calculate the dissolved oxygen mix. The dissolved oxygen mix. I will keep it here aside, that example. So dissolved oxygen mix, DO mix we have to calculate. DO mix is equal to formula, I will tell you, that dissolved oxygen of stream into discharge of stream plus dissolved oxygen of effluent into discharge of effluent upon QS plus QE. Okay, now we will put the value of the same. DO as saturated, is it? Sorry. DO of stream. How much is the DO of stream? It is the saturated one. We have taken it. It was DO 9.17 into QS. QS is the 1.2 plus DO of effluent is the 5 into QE is the 0.25 divided by 1.2 plus 0.25. When you will calculate this, you will get the answer 8.45. 8.45 milligram per liter. DO mix means what? Do you understood? So this way I have drawn the figure here. So once again I will show you that figure. Where is that paper? Here I have shown to you, at this particular spot you are allowing to dispose the sewage, and that stream is having their own water. The stream's characteristics are the different and the effluent's characteristics are different, but when you are disposing, it is getting mixed with each other, and then there will be the different characteristics. Here effluent, different characteristics. Upstream of this spot, the different characteristics of the stream, and when it is mixed here, there will be a different characteristics. That is nothing but the mixed characteristics. Is it? So that we are finding DO mix. After mixing the effluent into the stream, DO mix we have determined, that is 8.45. Okay. Now dissolved oxygen deficient, we have to find out that D is equal to dissolved oxygen deficient. How to find out? Dissolved oxygen deficient, we have given the notation. Initial dissolved oxygen deficient, D naught is equal to saturated level of dissolved oxygen is 9.17 minus actual level of that dissolved oxygen of that stream is 8.45. You will get the answer 0.72 milligram per liter is the initial dissolved oxygen deficient. Okay, now we will find out the Y mix. Y mix in the sense BOD of mix water. Mix water in the sense effluent and stream. Is it? And in the last sentence of your problem, it is suggested that the BOD is measured at 5 days. So instead of taking the Y mix notation, we will take the notation as Y5. It is 5, not the S. It is the Y5. So Y5 is equal to, the equation will be QS into YS plus QE into YE upon QS plus QE is equal to. So you will have to put the value of these. So what are the value of QS? QS is the 1.2 into YS 4 plus QE is the 0.25 into YE 20 divided by 1.2 plus 0.25. When you will calculate this, you will get the answer as 6.75 milligram per liter. You will get the answer 6.75 milligram per liter. So that is YS or Y mix. Is it? But about Y5 or the BOD, we know one more formula that we have studied again in a first chapter, BOD formula, first stage BOD formulation. Is it? So what is that formula? Y5 is equal to L naught into bracket 1 minus 10 raised to minus K into T. Is it? So here that we will put the value of all this. Y5 value is the 6.75 is equal to L naught into bracket 1 minus 10 raised to minus K. Value of K we have determined, given the value, that is 0.13 into T. T is the time of 5 days. So it is 5. Is it? So when you will calculate, you will get the value of L naught, and that value of L naught will be 8.71 milligram per liter. Is it? Okay. Now what we have to calculate? Finally we have to calculate the dissolved oxygen deficient at the point 20 kilometer and 40 kilometer. So which equation we have to go for? Dissolved oxygen deficient at dissolved oxygen deficient, DO deficient at 20 kilometer. First we will go for the 20 kilometer downstream. Okay, now we know the equation T is equal to distance upon velocity. Is it? So distance is given to us 20 kilometer. So 20 kilometer upon velocity is given to you. It is in a kilometer and velocity is given to you in a 0.18 meter per second. So I will rewrite this. T usually we calculate in a day. So I will go for the unit conversions. 20 into 1000. So it will become in a meter upon 0.18 meter into 60 into 60 into 24 meter per day. So meter gets cancelled and you will get the answer as 1.286 day. Is it? Now you can use the Streeter-Phelps equation. Streeter-Phelps equation. What is the Streeter-Phelps equation? That is dt is equal to k into L naught upon r minus k. We have just now solved that equation. That is 10 minus k into t minus 10 raised to minus rt into bracket complete d naught into 10 raised to minus r into t. We will put the value of all. That dt is equal to k. Value of k is the given. That value of k is given to you 0.13. 0.13 into L naught. L naught we have calculated. How much it is? L naught we have calculated. And it is the value of L naught 8.71 into 8.71 divided by r. R value of r is the 0.3 minus value of k 0.13. Is it? Into 10 raised to minus value of k 0.13 into t. Into t. How much t we should take now? T is the, we have calculated at 20 kilometer distance, t will be 1.286. Is it? Minus 10 raised to minus r. R value of r is 0.3 into t, again 1.286 bracket complete plus d naught. Value of d naught we have calculated. Is it? Value of d naught we have calculated and that is 0.72. Initial dissolved oxygen diffusion into 10 raised to minus r. Value of r is 0.3 into t 1.286. When you will calculate this, you will get the answer 2.089 milligram per liter. Dissolved oxygen deficient at 20 kilometer. Meanwhile, at the time 1.286 a day will be the 2.089 milligram per liter. Okay, this is about the 20 kilometer downstream. So with the same way you can calculate for the dissolved oxygen deficient. Dissolved oxygen deficient at 40 kilometer downstream. Is it? Another task. So here also t is equal to distance upon time. Sorry, distance upon velocity. So distance is equal to 40 kilometer upon 0.18 meter per second. When you will convert the units, you will get the value of t is equal to 2.572 days. Then put the value in a Streeter-Phelps equation. Again, Streeter-Phelps equation we have written here. That is dt is equal to k. K value of k is the 0.13 into L naught is the 8.71. So we have taken it here upon 0.3 minus 0.13 13 into bracket 10 raised to minus k is the 0 point. Value of k is the 0.13. Is it? 0.13 into t. What is the t now? Instead of 1.286, now we have to take the t at the 40 kilometer downstream, 2.572. Is it? Minus 10 raised to minus r 0.3 into 2.572. Bracket complete. Plus d naught. Value of d naught is the 0.72 into 10 raised to minus 0.3 into 2.572. When you will solve this, you will get the value of dt as 2.079 milligram per liter. So what is this? Dissolved oxygen deficient at time 2.572 day or 40 kilometer downstream from the effluent discharge. So this way you can determine the dissolved oxygen deficient. Okay, so this is about the analysis of the dissolved oxygen Sag curve. You might have understood. So few more examples we will try in the next lecture. Okay, so thank you very much.